A dusty archive holds notebooks filled with ideas that could have rewritten the laws of physics. These are the forgotten experiments, revolutionary investigations that promised to change everything but were lost to time. We are about to uncover 30 of these astonishing studies that should have altered our understanding of the universe forever. You will learn why brilliant discoveries are sidelined by technological limits, stubborn dogma, or simple bad luck. We will explore a case where flowing water hinted at Einstein's relativity decades early, and another where a scientist may have found a mysterious force that bends gravity itself. This journey reveals the hidden pathways science almost took, roads that might still lead to future breakthroughs. Are you ready to see how much of physics history has been left in the shadows in a cluttered Parisian laboratory? Hippolyte Fizeau set up a deceptively simple apparatus. Two beams of light were split, one sent racing with the flow of water through a glass tube, the other forced to fight against the current. The scientific establishment of 1851 was certain of one thing. Light was a wave, and like sound or ocean waves, it needed a medium to travel through. This invisible sea was called the luminiferous ether. Fizeau's goal was to catch the ether wind, to measure how this cosmic medium was disturbed by the moving water. He expected the light beam traveling downstream to get a speed boost from the current, while the upstream beam would be slowed down. The math was straightforward, or so it seemed. But the interference fringes, the delicate patterns of light and dark that revealed the difference in speed, told a stranger's story. The water did not simply carry the light along as a river carries a leaf. Instead, the light was only partially dragged, its speed changing by an amount that was puzzlingly small and precisely calculated. The result was an awkward fit for the popular ether theories of the day. It was a clue that the universe did not obey the simple rules of addition and subtraction when it came to light's velocity. This subtle anomaly was a whisper of relativity, a full half-century before Einstein gave it a voice. So why did this whisper not become a shout? Fizeau's experiment was celebrated for its precision, yet its deepest implication was politely set aside. It challenged a foundation of physics that few were ready to question. The ether was too comfortable an idea to abandon on the evidence of one complex experiment. Thus, a critical piece of the puzzle was left on the table, waiting for a future generation to recognize its true significance. This pattern of a brilliant discovery being just too inconvenient would repeat itself in a most dramatic fashion, with a lone astronomer who believed he had found a flaw in Newton's universal law of gravitation. While Einstein was reshaping reality in 1905, another brilliant mind was building a different path. Walter Ritz, a Swiss physicist, looked at the same puzzle and saw a completely different solution. He asked a simple but radical question: what if the speed of light was not a universal constant, but was tied to its source? In his emission theory, light behaved like a bullet fired from a gun. Its speed would be constant relative to the object that emitted it. This idea elegantly explained the famous Michelson-Morley experiment, which had failed to detect the mysterious ether wind. If light always traveled at the same speed relative to its source, then of course no experiment on a moving Earth could measure a difference. For a few years, Ritz's theory was a serious contender, a legitimate alternative to Einstein's strange new world of relativity. He developed complex and beautiful mathematics to support his vision, creating a coherent system that challenged the very core of emerging modern physics. The scientific community was presented with two competing realities, and the debate was fierce. But then came a test from the heavens themselves. Astronomers looked to binary star systems, where two stars dance around a common center of gravity. If Ritz was correct, the light from a star moving toward us would be emitted at a faster speed, while light from a star moving away would be slower. Over the vast distances of space, this would create a chaotic jumble of arrival times, distorting the observed orbits of these stars into an incomprehensible mess. The universe, however, presented clean, predictable orbits. The light arrived as if it had all traveled at the same speed, regardless of the motion of its source. Ritz's elegant theory was wrong, yet its dismissal came with an unintended cost. The intense intellectual battle it sparked, the rigorous scrutiny it forced upon Einstein's ideas, was invaluable. It was through this conflict that relativity was strengthened and refined. By forgetting Ritz's challenge, we lost the memory of that vital struggle, the process by which a good idea is forged into a great one by surviving a worthy opponent. This pattern of a valuable wrong turn leads us to another quiet challenge, one aimed at a constant so fundamental we rarely even think to question it. Yet even as the debate over Ritz's emission theory settled, the ghost of the ether refused to disappear entirely. High atop Mount Wilson, shielded from the warmth of the California lowlands, physicist Dayton Miller was conducting an experiment of immense patience and precision. While the names Michelson and Morley had become synonymous with the failure to detect the ether wind, Miller believed their famous experiment was not sensitive enough. He refined their interferometer, building a larger, more stable device made mostly of non-metallic materials to avoid temperature-induced distortions. For years, he meticulously recorded measurements, convinced he was hunting a signal so faint it required the clearest air and the most careful hand. And to his own certainty, he found it. Miller reported a small but consistent ether drift, a whisper of motion that seemed to align with the Earth's journey through space. This was not a null result. It was a direct challenge to the rising star of Einstein's relativity, which had done away with the ether entirely. The physics community was thrown into disarray. Miller was no fringe figure. He was a respected experimentalist with a flawless reputation. His data was extensive, his methods seemingly sound. For years, his results forced re-examinations and sparked heated controversies. How could such a careful scientist find evidence for something that theory said did not exist? The puzzle lingered, an uncomfortable anomaly that refused to be brushed aside. Ultimately, the consensus settled on a more mundane explanation. Later analyses suggested that the tiny signal Miller detected was almost certainly an artifact, not of the cosmos, but of his own apparatus. The very temperature variations he sought to avoid by building on a cold mountaintop may have subtly warped his equipment, creating the illusion of a drift. The ether was, once again, a mirage. But the story of Dayton Miller is less about a mistake and more about a stubborn question. What if his data had been correct? It demonstrates a profound tension in science, the conflict between a beautiful, dominant theory and a persistent, inconvenient piece of evidence. The process eventually self-corrects, but not before sidelining challenges that force a deeper scrutiny of accepted truths. This pursuit of a ghostly signal, a whisper from the edges of known physics, leads us to an even more radical search, one that sought not to revive an old idea, but to discover a completely new force of nature. Deep in the labyrinth of early 20th century physics, a principle was considered so unshakable it was rarely spoken aloud. It was the equivalence principle, the idea that gravity treats all objects equally. In a vacuum, a feather and a lead weight fall at the same rate because an object's gravitational mass, which feels the pull of gravity, is perfectly equivalent to its inertial mass, which resists being pushed. This simple truth is the bedrock of Einstein's general relativity. Yet, one man dedicated his life to testing this foundation with an almost obsessive precision. Hungarian physicist Laurent Eötvös designed an instrument of breathtaking sensitivity, the torsion balance. Imagine two different objects, perhaps a piece of wood and a chunk of platinum, hanging from the ends of a delicate rod, which itself was suspended by a fine wire. Eötvös understood that if the equivalence principle held, The gravitational pull of the Earth and the centrifugal force from our planet's rotation would balance perfectly for both objects. The rod would remain perfectly still, but if there was even the faintest difference in how gravity acted on the two substances, the rod would experience a tiny, twisting force. For decades, Eötvös and his team refined their measurements, achieving a level of accuracy that seemed almost supernatural for their time. They found nothing. The equivalence principle held firm, and their work became a legendary standard, a closed chapter in the book of physics. Then, nearly a century later, a team of researchers decided to take a second look at Eötvös's original data notebooks. They were not looking for an error but for a ghost, and they thought they found one. Buried within the numbers was a minuscule, almost imperceptible signal. It suggested that the force of gravity might, just might, be ever so slightly different depending on the composition of the object. It was not a failure of the experiment, but a hint of something new. A potential fifth fundamental force of nature to join gravity, electromagnetism, and the strong and weak nuclear forces. The physics world erupted. The idea of a fifth force was electrifying. Laboratories around the globe scrambled to build new, even more sensitive versions of Eötvös's torsion balance. For a few thrilling years, it seemed possible that a revolutionary discovery had been hiding in plain sight for generations. But the universe is a harsh judge. When the new experiments concluded, their results were definitive. There was no fifth force. The anomaly in Eötvös's data was almost certainly a statistical fluctuation, a random alignment of noise that looked like a signal, or perhaps an unaccounted-for local effect, like a subtle groundwater shift under his laboratory. The revolution was cancelled. Yet, this episode is far from a failure. It demonstrates a profound truth about scientific progress. The most important discoveries are not always new data, but new questions asked of old data. Eötvös's forgotten numbers, re-examined with fresh eyes, pushed experimental physics to a new extreme. They forced a generation of scientists to prove, beyond any shadow of a doubt, that a cornerstone of our universe was solid. This relentless drive to test the absolute limits of reality, to hunt for forces hidden in the tiniest of signals, would next turn its gaze from the Earth to the heavens, seeking to measure the very shape of empty space. While physicists were hunting for new forces, a Soviet scientist was uncovering a different kind of mystery, one hidden in the very noise of reality itself. In a laboratory in the 1950s, Simon Shnoll was conducting what should have been routine measurements, tracking the rates of simple chemical reactions or the decay of radioactive samples. He expected his data to follow a smooth, predictable pattern known as a Gaussian distribution, the familiar bell curve where most results cluster around an average value. But his charts told a different, far stranger story. The data points did not form a clean curve. Instead, they assembled into jagged, irregular shapes that looked more like mountain ranges than gentle hills. These distributions were not random. Day after day, Shnoll and his team observed that the specific shape of these jagged patterns would repeat. Even more astonishingly, the patterns seemed to change in sync with the cosmos. When measured at the same sidereal time, meaning relative to the distant stars as the Earth rotates, or at the same point in the Earth's orbit around the Sun, the bizarre shapes would reappear. It was as if the outcome of a simple chemical reaction in a Moscow lab was subtly influenced by our planet's journey through the galaxy. Shnoll proposed that these microscopic processes were being modulated by vast, unseen cosmological factors. The implications were staggering. It suggested that the universe is far more interconnected than we realize, that the random motion of a molecule might somehow feel the tug of a distant star. Mainstream physics, however, looked at these jagged graphs and saw not a cosmic connection, but a simple experimental error. The prevailing view was that Shnoll had failed to control for every possible variable, like minuscule temperature fluctuations or tiny vibrations from the city outside. His results were dismissed as statistical artifacts, the kind of pattern the human brain is wired to find in chaos, even when none exists. The Shnoll effect was relegated to the fringes of science, a curious anomaly too inconvenient to take seriously. Yet, it raises a profound and unsettling question. What if the randomness we take for granted in quantum mechanics is not random at all, but is instead a complex symphony orchestrated by forces we have yet to comprehend? This search for a hidden connection between the cosmos and the small-scale world leads to an even more controversial idea, one that dared to ask if human consciousness itself could be the missing link. The jagged patterns in Simon Shnoll's data suggested a universe where randomness might be an illusion. But what if that influence was not just cosmic, but conscious? This question drove physicist Helmut Schmidt to construct a machine that could listen to the human will. In the 1970s, while mainstream science was focused on quarks and quasars, Schmidt was designing an apparatus to test psychokinesis, the direct influence of mind over matter. He knew that for such a claim to be taken seriously, his method had to be flawless. His tool was a random event generator, or REG. Unlike a dice throw, which is chaotic but ultimately predictable with enough information, Schmidt's generators tapped into a source of pure, fundamental randomness, the quantum world. He used the process of radioactive decay, or, in later models, quantum tunneling, where a subatomic particle has a random chance of appearing on the other side of a barrier. Each quantum event was a perfect, unpredictable coin flip, generating a string of truly random ones and zeros. Schmidt's experiment was starkly simple. A person would sit in front of the machine, its output often displayed as a light that would flash for a 1 or stay dark for a 0. The subject's only task was to use their intention, their focused concentration, to will the light to flash more often or less often than pure chance would allow. They were not touching the machine, not creating vibrations, not generating heat. They were simply thinking. Over thousands upon thousands of trials, Schmidt compiled the data. The results were subtle, but to his analysis, they were undeniable. The streams of numbers were not perfectly random. They showed a tiny but statistically significant bias in the direction of the participants' intention. It was as if the human mind could whisper to the quantum world, and the quantum world, ever so faintly, whispered back. For Schmidt, this was not magic, it was physics. He proposed that consciousness might be a fundamental feature of the universe, capable of interacting with quantum probability waves, gently nudging chance toward choice. The implications were staggering, suggesting that the observer in quantum mechanics was not passive but participatory. The mainstream physics community, however, reacted with deep skepticism. The field of parapsychology was seen as a carnival sideshow, tainted by fraud and fantasy. Schmidt's rigorous protocols were dismissed as insufficient, his statistical methods questioned. The very idea of mind influencing matter was considered a violation of cherished physical laws. His work was pushed to the absolute fringe, a forbidden path that science was unwilling to walk. Yet, Schmidt's forgotten experiments leave behind a haunting legacy. They challenge the comfortable assumption that consciousness is merely a byproduct of the brain, an emergent phenomenon with no power over the physical world. What if his results were real? What if the barrier between the mind and the universe is far more porous than we dare to believe? This radical blurring of lines between the observer and the observed finds a strange parallel in another abandoned quest, one that sought not to unite mind and matter, but to merge the two great forces of the cosmos, gravity and light. While Helmut Schmidt was probing the edge where mind meets matter, another scientist was convinced he had found a new form of energy hidden within matter itself. In the glow of the early 20th century, as X-rays captivated the world, French scientist Gustave Le Bon announced a discovery that seemed even more miraculous. He called it black light. This was not the ultraviolet light we know today, but something far stranger. Le Bon claimed this radiation could pass effortlessly through thick sheets of metal, like lead or copper, that would instantly block ordinary light or even powerful X-rays. Most astonishingly, he reported that black light did not ionize the air it passed through. Unlike X-rays, which could electrify gases and fog photographic plates, black light was ghostly, leaving no detectable trace of its passage except for its ability to expose a photographic emulsion in the dark. For Le Bon, this was evidence of a profound new principle. He believed black light was a fundamental energy, a manifestation of the internal energy locked within the very structure of atoms, released as matter slowly disintegrated over time. It was a radical vision, suggesting that radioactivity was not a rare property of elements like radium, but a universal process happening all around us, albeit at an imperceptibly slow rate. The physics establishment, however, was deeply skeptical. Other researchers tried and failed to replicate Le Bon's results. His delicate experiments, which relied on long exposures and specific chemical preparations, were difficult to duplicate exactly. Many concluded that what he called black light was merely an artifact, perhaps a combination of scattered radiation, chemical phosphorescence, or subtle light leaks in his apparatus. Gustave Le Bon, once a celebrated popular scientist, was gradually pushed to the margins, his black light dismissed as a case of self-delusion or sloppy technique. Yet, from our modern vantage point, his forgotten work feels eerily prophetic. The concept of a penetrating, non-ionizing radiation that interacts weakly with normal matter is the precise definition of a neutrino, a particle that would not be confirmed for another 50 years. His idea of a universal energy within matter resonates with our current understanding of quantum vacuum fluctuations and dark energy. Le Bon was speaking a language that physics was not yet ready to understand, pointing toward phenomena for which the scientific vocabulary did not yet exist. His story is a powerful reminder that an idea can be premature, not false. This search for a hidden resonance within matter leads to another forgotten experiment, one that claimed to find a startling new force at the heart of the atom itself. The ghostly precision of quantum mechanics found one of its most perfect expressions in a young German physicist's frustration. Rudolf Mössbauer was a graduate student in the 1950s, trying to measure the gamma rays emitted by atomic nuclei. The problem he faced was fundamental. When a nucleus spits out a high-energy photon, it kicks back like a cannon, a tiny recoil that steals a small amount of energy from the emitted radiation. This recoil makes the gamma ray's frequency slightly unpredictable, a frustrating blur that limits how precisely it can be measured. Mössbauer was attempting to observe the reverse process, the resonant absorption of these gamma rays by other nuclei of the same type. But with the energy blurred by recoil, the effect was incredibly weak and difficult to detect. In a moment of inspired insight, or perhaps simple exasperation, he decided to try something different. He cooled his radioactive source to extremely low temperatures and embedded the atoms firmly within a crystal lattice. At this frigid state, the individual atoms could no longer recoil independently. The entire crystal, a massive object containing trillions upon trillions of atoms, had to absorb the kick. The recoil energy became vanishingly small, practically zero. The result was a beam of gamma rays of astonishing purity, a laser-sharp frequency so precise it could detect a change in gravity. This was the Mössbauer effect, a discovery that earned him a Nobel Prize just 3 years later. It became a universal tool, used to verify Einstein's prediction of gravitational redshift and to probe the magnetic fields inside materials. But the trail to this discovery was much older and littered with overlooked clues. Decades earlier, in the 1920s and 30s, scientists like Walter Kuhn and Sir Oliver Lodge had observed strange, sharp absorption lines in their experiments, anomalies they could not explain with the physics of their day. They saw the signal but lacked the key to decipher its meaning. The theoretical framework for understanding how an entire crystal could lock an atom in place was simply not yet mature. Those early observations were filed away as curiosities, unexplained glitches in the data. Imagine if just one of those researchers had possessed Mössbauer's insight. The entire timeline of 20th century physics might have accelerated. The incredibly precise tests of general relativity, which relied on the Mössbauer effect, could have been conducted sooner, potentially reshaping the acceptance of Einstein's theory. The techniques that now underpin materials science and medical diagnostics might have been developed a generation earlier. This was not a case of a failed experiment, but of a successful one that arrived too soon. Its significance hidden in plain sight until the right mind asked the right question. It is a story of a discovery waiting for its moment, a puzzle whose pieces were scattered and unrecognized until the final piece snapped into place. The beautiful, almost ethereal precision of Mössbauer's work stands in stark contrast to our next forgotten experiment, which dealt not with the quantum world, but with the immense, grinding forces that shape our planet itself. A high-voltage hum filled the laboratory as Thomas Townsend Brown watched his strange device. It was a simple object, really, just a pair of asymmetrical metal plates connected to a powerful electrical source, but he called it a gravitator. When he switched the current on, something extraordinary seemed to happen. The entire apparatus appeared to thrust forward, as if pushing against gravity itself. To Brown, working in the 1920s, this was not just an electrostatic quirk. He believed he had discovered a fundamental link, a direct coupling between electricity and gravity that he termed electrogravitics. He envisioned a future of silent, reactionless propulsion, where ships could defy gravity by manipulating these hidden forces. His gravitators, he claimed, were the first crude proof. The scientific establishment, however, heard only the crackle of ion wind. They explained the thrust as a simple, well-understood phenomenon. The intense electric field was ionizing the air molecules around the device, creating a stream of charged particles that pushed against the surrounding air, much like a miniature rocket exhaust. Since Brown's experiments were conducted in air, not a perfect vacuum, this explanation was perfectly sufficient to dismiss his grand claims. His electrogravitics was labeled a misinterpretation, an inventor's hopeful fantasy seeing a new law of physics in a known laboratory effect. The rejection permanently cast his work into the realm of fringe science, where it now fuels endless conspiracy theories about hidden government anti-gravity programs. Yet, the story of Thomas Townsend Brown is a crucial lesson in the sociology of science. It illustrates the immense difficulty of challenging core paradigms with an ambiguous effect. When a simpler explanation exists, even a brilliant anomaly is often dismissed. Brown's legacy is a haunting what-if, a question about whether he was a misguided tinkerer or a man who glimpsed a subtle truth that mainstream physics is still not equipped to see. This enduring mystery of a force that might bend the rules of propulsion finds a stark counterpoint in a far more concrete and deliberate challenge, one that took aim at the very heart of quantum theory and missed its mark. As the Copenhagen interpretation solidified into textbook dogma, a quiet rebellion was taking shape in the mind of Alfred Landé. While Niels Bohr and Werner Heisenberg spoke of wave functions collapsing upon measurement and the inherent strangeness of the quantum world, Landé sought a different foundation. He asked a disarmingly simple question: could the bizarre rules of the atom be derived from more reasonable, almost common-sense physical principles, without resorting to philosophical paradoxes? His approach was not a rejection of the mathematics, which he helped to develop, but a search for a different story to tell about what the math meant. Landé meticulously built up the quantum rules step by step, focusing on the necessity of discrete states and the prohibition of certain transitions. arguing that these were logical consequences of symmetry and simplicity rather than signs of a fundamentally irrational universe. He hoped to sidestep the deep unease of wave-particle duality and the role of the observer, offering a vision of quantum mechanics that emphasized continuity and causality. Yet, despite the mathematical sophistication of his work, it was drowned out by the rising tide of the Copenhagen school. Bauer's charismatic authority and the compelling, if bizarre, completeness of his interpretation created an intellectual momentum that was nearly impossible to resist. To be a quantum physicist in the 1930s was to speak the language of Copenhagen. Landé's alternative path was not so much refuted as it was ignored, a detour left unexplored on the map of physics. Today, however, his forgotten work resonates with a new urgency. As physicists grapple with the enduring mysteries of quantum theory, interpretations like de Broglie's pilot wave theory have gained fresh attention, suggesting that particles can have definite positions guided by a wave. In this new light, Landé's quest for a more intuitive, less paradoxical quantum foundation appears not as a failure, but as a missed opportunity. What if his approach had been given a fair hearing? Could decades of students have learned a quantum mechanics grounded in physical continuity rather than philosophical shock? This search for a tangible reality beneath the quantum haze leads directly to a bold experiment that attempted the seemingly impossible: to place light itself on a scale and weigh it. The triumph of Maxwell's equations seemed complete when Nichols and Hull confirmed a most delicate prediction. Light, for all its ethereal nature, must exert a tangible push. Inside a glass vacuum chamber, they suspended a tiny, mirrored vein with a thread so fine it could feel a whisper. They then allowed a beam of light to fall upon it. The challenge was monumental, as the force they sought to measure was smaller than the weight of a single bacterium. Any stray air current, any minuscule vibration from the world outside would drown the signal. Their success in measuring this radiation pressure was a landmark, a direct validation that light carries not just energy but momentum. It was a crowning achievement for classical physics. Yet, buried within their meticulous notebooks were other, stranger notations. As they refined their apparatus, they experimented with cooling their equipment to cryogenic temperatures and tried different reflective coatings on the vein. In some of these configurations, they recorded tiny, persistent deviations, forces that did not quite match the predictions of pure electromagnetism. These anomalies were small, easy to dismiss as experimental noise in the shadow of their grand success. The primary mission had been accomplished. Why dig deeper into confusing data that might only complicate a beautiful confirmation? So the subtler hints were set aside, filed away as curiosities rather than clues. The scientific machine, having achieved its goal, moved on. This pattern is a recurring danger in experimental physics. The very success of an experiment can blind us to its most intriguing failures. The data points that point towards something new. The quest to measure such imperceptible forces, to listen for whispers in the void, would next require an instrument of even greater sensitivity, one placed not in a laboratory vacuum chamber, but in the silent expanse between the stars. The year was 1903, and in a Dublin laboratory, Frederick Trouton and H.R. Noble prepared a device of elegant simplicity. They hung a parallel plate capacitor by a delicate quartz fiber, charged it with electricity, and set it in motion. Their goal was to feel the ether wind. According to the prevailing wisdom, the electric field lines between the charged plates should have been like invisible threads stretching through the stationary ether. As the Earth carried the entire apparatus through this cosmic medium, the moving ether should have pushed against those field lines, exerting a tiny twisting force, a torque, on the capacitor. The quartz fiber was sensitive enough to detect this minuscule rotation. They waited, they measured, and they found absolutely nothing. The capacitor remained perfectly still. It was a null result as definitive as the famous Michelson-Morley experiment. Yet their names are remembered only by specialists. Why did one null result become a cornerstone of physics while the other faded into obscurity? The Michelson-Morley experiment attacked the problem of the ether through the behavior of light, a central mystery of the era. Trouton and Noble, by contrast, approached it through the more esoteric realm of electrostatics. When Einstein's special relativity arrived 2 years later, it provided such a beautiful and complete explanation for the Trouton-Noble result that the experiment itself was quickly seen as merely a secondary confirmation, a puzzle already solved. It became a historical footnote, its own revolutionary potential forgotten. This selective memory of science reminds us that not all evidence is celebrated equally. We build monuments to the experiments that fit neatly into the triumphant narratives, while those that ask the same difficult question from a different angle are left by the roadside. Yet every null result, every silent answer, forces a deeper question. And sometimes, the most baffling experiments are not the ones that find nothing, but the ones that find a signal so strange it defies all expectation. Deep in the silent expanse between the planets, 2 robotic explorers were sending back a persistent, quiet whisper of wrongness. Pioneer 10 and Pioneer 11, having completed their missions to Jupiter and Saturn, were now coasting into the abyss. Meticulous tracking of their radio signals allowed NASA scientists to plot their trajectories with breathtaking precision. And there it was, a deviation so small it seemed almost insignificant, yet utterly confounding. Both spacecraft were experiencing a tiny, additional acceleration back toward the Sun. It was as if the ghost of solar gravity had reached out with an invisible hand, giving them an extra, imperceptible tug. This was the Pioneer Anomaly, and for years it was one of the hottest puzzles in physics. The unexplained force was minuscule, comparable to a 10/1000th of the gravity you feel standing on Earth, but it was undeniably there. The implications, however, were colossal. Could this be the first crack in Einstein's theory of general relativity? Was it evidence of a halo of dark matter surrounding our solar system, subtly altering the laws of motion? Perhaps it pointed to a modification of inertia itself at extremely low accelerations. The anomaly sparked a firestorm of theoretical papers, each proposing a revolutionary new piece of physics to explain the data. It was a golden age for cosmic speculation, fueled by a real, tangible mystery from the depths of space. The solution, when it finally arrived, was a masterpiece of scientific humility. A team of researchers embarked on a digital archaeology project, recovering decades-old engineering data and building an exquisitely detailed computer model of the Pioneer spacecraft. They considered every conceivable factor, especially the gentle but constant heat radiating from the spacecraft's nuclear power generators and its internal electronics. Their model revealed the culprit. Heat was not radiating away from the spacecraft uniformly. A slightly greater amount of thermal photons were bouncing off the back of the large dish antenna, pushing back toward the Sun with just enough force to account for the anomalous acceleration. It was not new physics, it was old physics, applied with a new level of meticulous care. The Pioneer Anomaly was solved, and in being solved, it was promptly forgotten, relegated to a footnote as a problem that turned out to be conventional. But to dismiss it is to miss the profound lesson. The real discovery was not in the anomaly itself, but in the painstaking process of ruling out every last mundane possibility. It stands as a monument to the principle that extraordinary claims require extraordinary evidence, and that the most seductive cosmic mysteries are sometimes hiding in the plain sight of an unaccounted-for watt of heat. This triumph of careful analysis over sensational speculation finds a stark contrast in a laboratory mystery that has, so far, stubbornly refused to yield any such tidy explanation. A spinning disk of ceramic, chilled to near absolute zero and levitated by powerful magnets, was at the heart of an announcement that sent shockwaves through the physics world. In the 1990s, Russian materials scientist Evgeny Podkletnov claimed this superconducting apparatus was not just a marvel of materials science, but a gravity shield. He reported that small objects placed directly above the rapidly spinning disk experienced a minute but measurable reduction in their weight, as if a fraction of Earth's pull had simply been cancelled out. The implications were staggering. This was not science fiction anti-gravity, but a potential new property of superconductors interacting with the gravitational field, a phenomenon that could rewrite textbooks and open the door to technologies beyond imagination. The immediate reaction was a mix of intense skepticism and frantic, secretive interest. Major aerospace corporations and government agencies, lured by the revolutionary potential, quietly launched their own replication efforts. The problem was, no one could get it to work. Independent labs, following Podkletnov's published methods as closely as they could, found no evidence of any weight loss. The scientific consensus swiftly hardened. Podkletnov's result, it was concluded, was almost certainly an artifact. The complex setup involved powerful magnetic fields and rapidly moving air currents, either of which could easily produce a tiny, deceptive force that mimicked a reduction in gravity. Furthermore, the very idea of a gravity shield struck at the heart of general relativity, which describes gravity not as a force that can be blocked, but as the curvature of spacetime itself, a geometric effect that permeates everything. You cannot shield an object from the shape of the universe. The Podkletnov affair stands as a stark lesson in the rigorous demands of the scientific process. An extraordinary claim requires not just evidence, but evidence that can be reproduced by skeptical outsiders under controlled conditions. When such replication fails repeatedly, the claim is set aside. Yet, even as a cautionary tale, it highlights a critical tension. The line between a visionary discovery and a meticulous error can be impossibly fine. Podkletnov's work was isolated and dismissed, a fringe idea pushed to the margins. But it forces a difficult question. What if the failure to replicate was not because the effect was false, but because it was far more subtle and fragile than anyone realized, dependent on a specific, unreproduced condition in the superconductor itself? This controversy over a cosmic force measured in a lab gives way to a far quieter investigation, one that sought to measure the grandest motion of all, the expansion of the entire universe, from a small telescope in a Washington, D.C. attic. Arthur Eddington's name is forever linked with a moment of scientific triumph, that day in 1919, when he confirmed the bending of starlight by the sun. Yet for the remaining decades of his life, the celebrated astronomer embarked on a far more solitary and speculative quest. He became consumed by a desire to build a fundamental theory, a single edifice of thought that would house both the vast cosmos of relativity and the ghostly rules of the quantum world. But his method was radically different from anything that had come before. Eddington believed the key to the universe was not in complex experiments, but in the purity of numbers themselves. He became convinced that the fundamental constants of nature, like the fine structure constant that governs the strength of electromagnetic interactions, were not arbitrary. To him, they were mathematical inevitabilities, values that could be derived from first principles through a form of logical and almost numerological deduction. He worked tirelessly, filling notebooks with intricate calculations aimed at showing that the number 137, the approximate inverse of the fine structure constant, was a necessary result of the universe's very structure. To his colleagues, who had revered him for his empirical rigor, this was a bewildering and tragic shift. The man who had provided one of the strongest experimental proofs for Einstein was now seemingly abandoning experimentation altogether, retreating into a world of abstract numeracy that looked more like mysticism than physics. His fundamental theory was politely ignored, then largely forgotten, dismissed as the misguided obsession of a great mind in decline. Yet, to write off Eddington's later work is to miss its profound significance. It stands as a powerful monument to the human desire for a complete and elegant explanation of reality. He was searching for a universe that made sense not just in its operation, but in its very essence, a cosmos built on a beautiful, logical foundation. His failure reminds us that the path to unification is fraught with peril, and that even the most brilliant intellects can be led astray by the siren song of a perfect theory. But his ambition, the sheer audacity to believe that the deepest secrets of physics could be unlocked by pure thought, continues to inspire. This drive to find a single, simple rule governing all of existence would not die with Eddington. It would resurface in the work of another visionary, one who also believed he had found a key to the cosmos hidden in plain sight, etched into the very fabric of space and time. The stage was set for a philosophical war at the 1927 Solvay Conference, the most elite gathering of physicists the world had ever seen. A young Louis de Broglie stood before titans like Einstein, Bohr, and Heisenberg, proposing a radical alternative to the emerging quantum orthodoxy. He called it the pilot wave theory. In this elegant vision, particles were not probabilistic ghosts. They were real, tiny objects with definite positions at all times, but they were not alone. Each particle was guided by a pilot wave, a real physical wave spreading through space that dictated its path. This single idea resolved the central paradox of quantum mechanics. The famous double-slit experiment, where a single electron seems to interfere with itself, was no longer a mystery. The electron was simply a particle riding its guiding wave through both slits, its trajectory determined by the wave's interference pattern. It was a picture of stunning clarity, a deterministic universe hiding beneath the veil of probability. The reaction from Niels Bohr was swift and devastating. Bohr, the architect of the Copenhagen interpretation, saw de Broglie's theory as a retreat to a discredited classical past. He believed the wave was not a real guide, but merely a mathematical representation of our knowledge. For Bohr, the inherent uncertainty, the fundamental role of the observer in collapsing the wave function, was not a bug but a feature of reality. Under the intense pressure from Bohr and his allies, de Broglie, a relatively junior figure, faltered. He abandoned his own brilliant idea, leaving it to gather dust for a generation. It was only resurrected in the 1950s by the courageous physicist David Bohm, who refined and defended it against a now hostile establishment. But by then, the battle was already lost. The Copenhagen interpretation had become the unquestioned dogma, written into every textbook. The road not taken by de Broglie leads to a profound what-if. What if his pilot wave theory had been given a fair hearing? Our entire philosophical conversation about quantum mechanics would be different. Instead of a century spent debating cats that are both dead and alive, we might have focused on a world that is deterministic but deeply non-local, where particles whisper to each other across vast distances. The suppression of this idea at its birth shows how the weight of authority can alter the course of science itself. This struggle over the fundamental nature of reality finds a strange parallel in a much later experiment, one that dared to challenge a constant even more sacred than causality, the speed of light. Georges Sagnac was certain his spinning table had caught the ether at last. In a Paris laboratory in 1913, he constructed a beautifully simple device. A beam of light was split in two, with each half sent racing in opposite directions around a closed rectangular path made of mirrors, all mounted on a platform that could be rotated. When the platform was still, the two beams of light, having traveled the same distance, would reunite in perfect sync, their waves aligned. But when Sagnac set the table spinning, the result was a dramatic shift in the interference pattern. The beam traveling with the rotation had to chase a mirror that was moving away, while the beam going against the rotation met its mirrors sooner. This created a measurable difference in the time it took for each light beam to complete the loop. For Sagnac, this was undeniable proof. He had detected a drift, a cosmic current. The stationary ether was there, and his rotating apparatus was moving through it. He declared victory for the old physics. Yet, just a few years later, Einstein's general relativity offered a completely different explanation, one that required no ether at all. In Einstein's universe, the rotating platform was not moving through an invisible medium, but was instead twisting the very fabric of spacetime around it, an effect known as frame dragging. The light beams were simply following the contours of this warped geometry. Sagnac's experimental result was correct, but his interpretation was a ghost from a fading era. His ether-based explanation was quietly forgotten, a historical curiosity, but the experiment itself refused to fade away. The Sagnac effect became the foundational principle for a revolutionary piece of technology, the ring laser gyroscope. Inside every modern aircraft and spacecraft, beams of light race in opposite directions around a closed loop, exactly as in Sagnac's original setup. The slightest rotation of the craft creates a tiny shift in the interference pattern, allowing the navigation system to detect changes in direction with incredible precision, all without any moving parts. It is a perfect paradox of scientific progress. Sagnac was right about what he saw, but wrong about what it meant, and yet his misunderstood experiment now guides us safely across the globe. This dance of light on a rotating stage demonstrates that a useful truth can be discovered even when its deepest meaning remains hidden. This interplay between rotation and fundamental forces would next be explored on a far smaller, yet equally profound, scale within the heart of the atom itself. The clattering vacuum pumps and faint hiss of escaping gas were the soundtrack to a different kind of quest. While some searched for cosmic forces, others aimed their instruments inward, toward the mysterious heart of the atom itself. In university laboratories during the 1930s, a handful of physicists attempted an almost surgical procedure. They sought to measure the magnetic personality of the atomic nucleus, to see if it acted like a tiny bar magnet. Isidore Rabi was among these pioneers, guiding beams of molecules through intensely powerful magnetic fields. The principle was straightforward. If the nucleus had a magnetic moment, the field would tug on it, deflecting the beam's path by a minuscule but measurable amount. The reality, however, was a lesson in frustration. Their vacuum chambers were not perfect, allowing stray gas molecules to crash into and scatter their delicate molecular beams. Their methods for creating and controlling these beams were primitive, leading to inconsistent and often contradictory results. A successful run one day would be followed by inexplicable failure the next. These early nuclear bar magnet experiments were the clumsy, necessary ancestors of a revolution. They were the messy groundwork, the trials that taught physicists precisely what not to do. Every failed deflection, every uninterpretable blur on a detector screen, was a lesson in what technology was missing. The struggle itself defined the path forward, proving that success required a leap in vacuum technology and beam control that would not arrive for another decade. Rabi himself would eventually pioneer that leap, developing the elegant method of nuclear magnetic resonance that earned him a Nobel Prize. But we rarely celebrate the fumbling first steps that made the elegant victory possible. These forgotten experiments remind us that scientific progress is not a series of brilliant leaps, but a slow, painstaking crawl through a wilderness of error. This stark contrast between messy groundwork and a polished breakthrough sets the stage for a claim that was all bold leap and no crawl at all. A glass vial of pure water sat at the center of a scientific scandal that would rock the world of immunology. In 1988, Jacques Benveniste, a respected French researcher, made an extraordinary claim. He stated that an antibody solution, diluted again and again until not a single molecule of the original substance remained, could still trigger a biological response. The water, he argued, remembered the shape of the molecule it had once contained, like a liquid ghost holding onto a vanished imprint. This was the controversial foundation of homeopathy, seemingly given validation in the pages of the prestigious journal Nature. The outcry was immediate and fierce. How could water have a memory? The established laws of chemistry offered no mechanism for such an effect. In response to the furor, Nature took an unprecedented step. The editor dispatched a team to investigate Benveniste's lab, a team that included the renowned magician and skeptic James Randi. Their conclusion was devastating. They alleged that the experiments were riddled with unconscious bias, poor statistical analysis, and a lack of proper blinding, meaning the experimenters could have influenced the results simply by knowing which samples were which. The paper was retracted, and Benveniste's reputation was ruined, his work held up as a prime example of pathological science. Yet, buried beneath the accusations of fraud and poor practice, a tantalizing question refused to die. What if the effect, however faint, was real, but for reasons no one had considered? A small group of researchers, working far from the mainstream, began to explore the idea that water's structure is not random. They proposed that complex networks of hydrogen bonds could form stable, long-lasting patterns, perhaps capable of storing information in a way that transcends simple chemistry. This fringe field of study, investigating water's potential interactions with electromagnetic fields, remains deeply controversial and largely ignored. The Benveniste affair serves as a stark lesson in the self-correcting nature of science, but it also highlights a deep tension. When an anomaly challenges fundamental assumptions, the line between a groundbreaking discovery and a profound error can be razor-thin. This search for a memory etched into a simple substance leads to an even more ambitious idea, an attempt to listen for an echo of creation itself, a memory frozen into the fabric of the cosmos. High above the Earth, suspended from balloons or mounted on the noses of captured German V-2 rockets, a new generation of detectors scanned the darkness between the stars. They were not looking for starlight, but for a far more elusive glow. In the 1950s, physicists hunting cosmic rays wondered if the void itself could shine. Their target was Cherenkov radiation, that unearthly blue light seen in nuclear reactor pools, created when a charged particle outruns light itself within a medium like water. Theorists speculated that the vast expanse of space was not entirely empty. The thin gas and dust of the interstellar medium, they reasoned, could act as a cosmic pond. An ultra-high energy particle, a proton accelerated to nearly the speed of light by a distant supernova or quasar, might punch through this tenuous gas fast enough to create a shockwave of light, a faint, fleeting Cherenkov flash in the galactic deep. These early experiments were acts of profound optimism. They aimed to transform the entire galaxy into a natural particle detector, using this faint radiation to map the invisible rain of cosmic rays. But the signal they sought was a whisper against a roaring background. The glow was too diffuse, the instruments too crude. The cosmic static and the sheer faintness of the expected light made any definitive detection impossible. The promising idea was set aside, a road not taken in the rush toward more direct methods of particle detection. Yet, this forgotten avenue of research now seems prescient. Imagine what a modern space telescope, with its exquisitely sensitive detectors and advanced optics, might see if it were trained on this specific question. That faint, diffuse glow, if it could be captured, would be a direct window into the most violent events in the universe, a way to trace the paths of particles with energies far beyond anything we can create on Earth. It was a search for a ghost of light, a signature written in the dark. This ambition to listen to the faintest echoes of the cosmos would next take a far more literal form, as scientists built an antenna to hear the birth of time. Robert Dicke was already listening for the echo of creation, while Arno Penzias and Robert Wilson were famously puzzled by a persistent hiss in their horn antenna at Bell Labs. A team at Princeton University, led by Dicke, was actively building the instrument designed to hear it. Dicke had resurrected an old idea, the notion of a hot, dense beginning to the universe, and deduced that if such a Big Bang had occurred, the entire cosmos should be filled with a faint, cold glow of radiation, a relic heat from the initial fireball. He called this the primeval fireball and tasked his team with constructing a delicate radiometer to scan the skies for its signal. They were in a deliberate, calculated race against time, calibrating their equipment with meticulous care. Then came the phone call. Penzias and Wilson, having exhausted every possible explanation for the annoying background noise in their antenna, contacted Dicke to ask if he had any ideas. Dicke hung up the phone, turned to his team and said simply, "Well, boys, we've been scooped. The discovery of the cosmic microwave background radiation would earn Penzias and Wilson the Nobel Prize, and Dicke is rightly honored for his crucial theoretical prediction." But the fact that he had an experiment already poised to make the same discovery is a forgotten chapter. It was a near miss measured in mere months, a stark reminder that in science, the ribbon is cut for the one who crosses the finish line first, even if someone else laid the track and was racing right behind. This story of a search that was almost simultaneous with its success highlights how fragile the timeline of discovery can be, dependent on luck and circumstance as much as on brilliance. From this echo of the universe's birth, we plunge into the quantum realm, where another brilliant mind offered a different kind of map, one that was largely ignored for a generation. John G. Cramer offered a handshake across time to resolve the quantum dilemma. In the 1980s, while most physicists were content to use the mathematics of quantum mechanics without worrying too much about the bizarre reality it described, Cramer proposed a radical new picture. He called it the transactional interpretation. Imagine an electron is about to be emitted from a source. According to Cramer, it first sends out an offer wave, a ripple moving forward in time that spreads out in all directions, exploring every possible path. When this wave reaches a potential detector, say a photographic plate, the detector responds by sending a confirmation wave backward in time, retracing the path of the offer wave. Only when these two waves, one going forward and one going backward, meet and reinforce each other does the transaction become complete. The electron is finally emitted, but its path is already set by this strange, timeless agreement. This elegant handshake explains the infamous double-slit experiment with stunning clarity. The offer wave travels through both slits and interferes with itself, creating a pattern of possibilities. The confirmation wave, coming from the future detector, selects which part of that pattern will be reinforced, determining where the electron appears. There is no mysterious collapse of the wave function, no need for parallel universes. It is a single, self-consistent process that treats time as a two-way street. So why did this beautifully simple idea fail to capture the imagination of physics? The answer lies in its most daring ingredient, retrocausality. The confirmation wave moves backward in time, meaning the effect, the detector's response, can precede the cause, the emission of the particle. This notion violates our deepest intuition about how reality should operate. Cause must come before effect. It is the fundamental rhythm of our existence. For most scientists, accepting retrocausality felt like surrendering to nonsense, even if the math worked perfectly. Cramer's interpretation was therefore sidelined, viewed as a clever but ultimately fantastical solution to a problem that other interpretations tackled without turning time upside down. It remains a ghost in the quantum machine, a reminder that the most logical answer can be rejected simply because it feels wrong. This challenge to our linear experience of time sets the stage for an experiment that appeared to break causality not in theory, but in a measurable physical way. A simple flick of the wrist became the center of a revolution in our understanding of the mind. In a series of now famous experiments during the 1980s, neuroscientist Benjamin Libet asked participants to perform a trivial act, like flexing their finger while watching a fast-moving clock. Their only complex task was to note the exact moment they felt the conscious urge or decision to move. Meanwhile, electrodes monitored their brain activity. The results were deeply unsettling. Libet discovered a specific electrical signal in the brain, which he called the readiness potential, that appeared a few hundred milliseconds before the person was even aware of their own intention to act. It was as if the brain had made the decision before the conscious mind was informed. This tiny delay suggested a profound reordering of cause and effect. Our feeling of free will, of being the author of our actions, might be an illusion, a story the brain tells itself after the fact. The implications ripple far beyond neuroscience into the foundations of physics. For decades, a central puzzle of quantum mechanics has been the role of the observer. The act of measurement, of conscious observation, is said to collapse a probability wave into a definite reality. But if Libet is correct, what does it mean for a conscious observer to make a measurement if their own conscious decisions are preceded by unconscious brain activity? The very idea of a conscious cause becomes tangled and paradoxical. The debate over Libet's experiments is fierce. Some argue the readiness potential is merely background noise, not a true decision signal. Others question the subjective timing of the conscious urge. Yet, the door he opened remains ajar, a crack of light between the deterministic world of physics and the mysterious realm of subjective experience. It forces us to ask if our most fundamental sense of agency, the feeling that we are in control, might be the ultimate forgotten variable in our equations of reality. This unsettling question of timing and intention finds a strange counterpoint in a purely physical clock that seemed to defy explanation, a timing anomaly that emerged not from the human brain, but from the silent decay of atomic nuclei. For decades, a faint but persistent tremor ran through the foundations of particle physics, centered on a particle called the muon. Think of the muon as a heavier, unstable cousin of the electron, spinning on its axis like a tiny top. This spin gives it a magnetic personality, a strength measured by a value known as its G-factor. According to the immensely successful standard model of particle physics, this value should be almost, but not quite, 2. The tiny difference, called the anomalous magnetic moment, is a delicate dance where the muon interacts with a cloud of virtual particles constantly popping in and out of existence. Throughout the late 20th century, as experimentalists built more precise machines to measure this anomaly and theorists performed more complex calculations to predict it, a small gap remained. The experimental number never quite matched the theoretical one. The discrepancy was slight, often within the stated margins of error for both sides. It was the kind of result that could be explained away, attributed to unaccounted for uncertainties in the labyrinthine math or to subtle, undetected flaws in the apparatus. So, for years, this nagging anomaly was politely shelved, noted in papers but not seen as a crisis. It was a whisper in a noisy room, easy to ignore. But whispers can accumulate. The recent headline-making results from Fermilab's G2 experiment are not a sudden discovery. They are the culmination of this long, quiet history. They represent the moment the whisper became a shout, when technology finally advanced enough to reduce the uncertainties to a point where the anomaly could no longer be dismissed. The muon has been trying to tell us something for generations, hinting at particles or forces beyond our current model. We simply lack the precision to listen properly. This story of a long-ignored signal finally gaining a voice finds a stark contrast in a search that began with a bang. an experiment that hoped to find an enormous new force emanating from our own planet. Long before the first official SETI program scanned the skies, the hiss of an empty radio channel sparked a profound hope. In the 1920s, as commercial radio began to connect the world, a strange phenomenon occurred during moments of exceptional atmospheric quiet. Engineers and amateur radio enthusiasts, tuning their crackling sets between stations, would sometimes encounter a persistent, unidentifiable static. With no earthly source apparent, a tantalizing idea whispered through the community. Could this be it? Could this steady, cosmic noise be a signal from another world, bleeding through the void into our headphones? These early listeners were the Daytonian searchers, named for the day they dared to believe the stars might be speaking. They lacked the sophisticated receivers and computer algorithms of modern SETI. Their tools were primitive, their methods informal, little more than curious notations in a logbook. When the unexplained static faded with the rising sun or an increase in local interference, the mystery was usually set aside, chalked up to an unknown atmospheric effect or a flaw in the equipment. It was a search born of intuition, not rigorous protocol. These forgotten moments represent a fundamental human impulse, the longing to know we are not alone in the vast silence. They were the first, fumbling attempts to answer the oldest question, a question that technology was not yet ready to properly ask, let alone answer. This quiet listening to the cosmos stands in stark opposition to an experiment that aimed its receiver in the opposite direction, not toward the stars, but deep into the ground beneath our feet. The destructive power of the atom bomb held a strange promise for the future of spaceflight. In the shadow of the Manhattan Project, two of its architects, Emil Konopinski and Stanislaw Ulam, turned their minds from weaponry to wonder. They envisioned a spacecraft unlike any other, a vessel propelled not by the controlled burn of chemical rockets, but by the raw, unadulterated fury of nuclear fire. Their design was breathtakingly simple in concept, yet almost unimaginable in its audacity. The ship would eject a small atomic bomb out of a stern-mounted launch tube. Moments later, the bomb would detonate. The resulting blast wave, an expanding sphere of incandescent plasma, would slam into a massive, heavily shielded pusher plate attached to the ship. A system of giant shock absorbers would translate that unimaginable force into a forward push, hurling the spacecraft onward before the process repeated. Bomb after bomb, explosion after explosion, a continuous series of controlled blasts would create a form of nuclear pulse propulsion. This was Project Orion, and on paper, it was not science fiction. The calculations suggested it could achieve speeds impossible for conventional rockets, potentially carrying entire cities' worth of people on voyages to Saturn within a matter of months. It was a vision of space exploration built on sheer, overwhelming power. But the dream collided with a grim reality. The 1963 Partial Test Ban Treaty outlawed nuclear explosions in the atmosphere and outer space, effectively grounding Orion before a single test flight could occur. Beyond the politics lay a more visceral fear. The image of a spacecraft rising into the heavens on a pillar of radioactive fallout, seeding the very void it sought to explore with deadly contamination. The project was shelved, its blueprints filed away as a monument to a path not taken, a future where humanity rode shockwaves to the stars. This brute force approach to physics stands in stark contrast to our next experiment, which sought to harness not a stellar explosion, but a subtle, almost musical vibration within the heart of a solid crystal. A simple glass rod rubbed with silk seemed like child's play, but it held the key to a profound connection. In the mid-19th century, physicists like Ottaviano Mossotti and Rudolf Clausius were obsessed with a deceptively simple question. How does a material as a whole respond to an electric field? They knew that inside an insulating substance, individual molecules could be distorted, Their positive and negative charges tugged in opposite directions, a property called polarizability. Mossotti and Clausius sought a mathematical bridge, a way to predict the bulk behavior of a material, its dielectric constant, from the microscopic properties of its constituent parts. The formula they derived, the Clausius-Mossotti relation, is a thing of elegance, a clean line connecting the invisible world of atoms to the measurable property of a block of matter. It sits proudly in textbooks today, a settled piece of physics. But before it was an equation in a book, it was a battlefield of uncertainty. The first experimental attempts to verify this relationship were exercises in frustration. The materials available to 19th-century scientists were far from pure. A sample of sulfur or glass might contain unseen impurities that drastically altered its electrical properties. Their measuring instruments were crude and susceptible to environmental factors like humidity and temperature, a result that seemed to confirm the relation one day would be contradicted the next. These early researchers were not confirming a known law, they were groping in the dark, trying to discern a signal through a storm of noise. Their forgotten notebooks are filled with contradictory data, crossed-out calculations, and puzzled marginal notes. We remember the clean, triumphant formula, but we have erased the messy, human struggle that made it credible. This journey from chaotic experiment to crystalline law is a pattern repeated throughout physics, a reminder that our surest truths were once shrouded in doubt. And if determining the properties of a solid block of wax was so difficult, what hope could there be for measuring the properties of nothing at all? This question leads to an experiment that attempted to do just that, to probe the emptiness of the vacuum for a hidden structure. The empty space between atoms was once thought to be a perfect void, a stage where particles performed their quantum dances, but a few early 20th century physicists suspected it was something more. They wondered if a perfect vacuum could act like a subtle, ethereal version of a block of wax or glass, a medium that could be electrically polarized. Their reasoning was an intuitive leap. In a classical dielectric material, an external electric field tugs on the internal charges, creating a slight separation that opposes the field's own force. If the vacuum itself contained a sea of virtual particle-antiparticle pairs, constantly flickering in and out of existence as quantum theory would later suggest, then perhaps an intense electric field could also polarize this sea. The vacuum, they hypothesized, might have its own dielectric constant, a measure of how it would respond to such a field. They designed experiments of exquisite sensitivity, attempting to measure the most minuscule change in the capacitance of a vacuum capacitor when subjected to enormous voltages. They were searching for a whisper of resistance from the void itself, a sign that empty space was pushing back. But their instruments, however precise for their time, were hopelessly crude for the task. The quantum effect they were intuitively chasing, which we now call vacuum polarization, is so incredibly tiny that it only becomes significant in the ferocious electric fields near an atomic nucleus or in the collisions of high-energy particles. Their classical tools were like trying to hear a pin drop from a mile away with the naked ear. They found nothing but the silence they expected, and their attempts were forgotten, filed away as failures. Yet, these forgotten experiments reveal a profound pattern in how science progresses. Faced with a mystery, the human mind first tries to fit it into an existing box. These physicists were not wrong to think of the vacuum as a medium, they were just premature. Their classical intuition was a stepping stone, a flawed but necessary attempt to grasp a truth that required a completely new language, the language of quantum field theory, to be properly understood. This struggle to measure the imperceptible properties of nothing finds a stark contrast in a quantum experiment that succeeded brilliantly, yet remains overshadowed by its more famous cousin. Light itself seemed to be misbehaving in the clear night sky over Narrabri, Australia. Astronomers Robert Hanbury Brown and Richard Twiss had devised a brilliantly simple method to measure the unimaginable, the true diameter of distant stars. Instead of using the traditional and incredibly difficult approach of measuring the phase of light waves with a standard interferometer, they focused on something far more straightforward: its intensity. They placed two separate light detectors, large mirrors collecting starlight, a considerable distance apart. Each detector simply recorded the random flickers in the brightness of the star, the noisy dance of individual photons arriving from across the light years. On their own, these two signals were just meaningless static. But when Hanbury-Brown and Twiss correlated them, when they looked for a subtle relationship between the twinkles at one detector and the twinkles at the other, they found a startling connection. The flickering was not completely random. The photons had a tendency to arrive in bunches, creating a faint but measurable correlation between the two separated detectors. The width of this correlation peak directly revealed the angular size of the star. It was an elegant solution to an ancient problem. The physics community, however, reacted not with applause, but with disbelief and outright hostility. To many leading theorists, including several Nobel laureates, this Hanbury-Brown and Twiss effect seemed to violate the very heart of quantum mechanics. The prevailing wisdom held that photons, the particles of light, were independent entities that did not interact with one another. They should arrive at the detectors like random raindrops, with no tendency to cluster together. The idea that photons could exhibit this kind of bunching behavior was dismissed as impossible, a clear sign that the astronomers had made a fundamental error in their analysis. The controversy raged for years, a classic clash between clear experimental data and entrenched theoretical dogma. How could two photons, emitted at different times from a star millions of miles wide, know to arrive at Earth in sync? The answer, when it finally came, was a profound lesson in quantum statistics. Photons are bosons, a class of particles that actually prefer to be in the same state. This bunching was not an error. It was a signature of their quantum nature, a collective identity that becomes visible when you stop looking at them as individuals and start looking at the crowd. The initial rejection of the Hanbury-Brown and Twiss effect sidelined a powerful technique for years, a delay driven by the difficulty of accepting that the quantum world could be stranger than our intuition allowed. This quest to find connection in apparent chaos, to see a hidden order in the behavior of distant particles, brings our journey to its final and most ambitious forgotten experiment. The first attempts to trap quantum strangeness in a laboratory were humble affairs, far from the polished experiments we know today. John Stuart Bell had thrown down a gauntlet in 1964, offering a mathematical test, an inequality that could settle a philosophical debate once and for all. He asked if the spooky connections of the quantum world were real or just an illusion. On one side stood Einstein's belief in a local reality, where no influence could travel faster than light. On the other was the bizarre non-locality suggested by quantum theory, where measuring one particle could instantly affect its distant twin. Bell's theorem was a recipe for an experiment, a way to force nature to choose. Into this breach stepped John Clauser and Stuart Friedman in the early 1970s. Their apparatus was a masterpiece of ingenuity built on a shoestring budget. They used calcium atoms as a source of entangled photons, pairs of light particles whose fates were linked. It was a delicate, finicky setup, a far cry from the sleek lasers and cryogenic systems used today. The calcium had to be heated in an oven, the photons carefully channeled through polarizers to detectors that clicked with each arrival. Every part of the system was a potential source of error, a loophole through which a more conventional explanation could escape. And indeed, their results, while leaning decisively in favor of quantum mechanics, were not the final word. The detectors were slow, meaning one particle could, in theory, send a signal to its partner at the speed of light before a measurement was completed. The source of the particles was not perfectly efficient. These were the known loopholes, the acknowledged weaknesses that kept the debate alive. Clausius and Friedman knew their work was not the end of the story, but the essential, gritty beginning. They were the pioneers who proved such a test was even possible, who faced the skepticism of a community still uneasy with quantum weirdness. Their forgotten struggle is a vital chapter in the story. We remember the triumphant, loophole-free experiments of Elaine Aspect a decade later as the definitive proof, but they stood on the shoulders of these first, courageous attempts. This reminds us that a scientific revolution is rarely a single, blinding flash of insight. It is a slow dawn, built by those who are willing to work in the dim light of imperfect apparatus and uncertain results, paving the way for the clarity that follows. The journey through these forgotten experiments reveals a landscape shaped as much by silence as by sound. Time and again, a brilliant idea fades not because it is false, but because its moment has not yet come. It is a history of whispers drowned out by the noise of consensus, of paths abandoned not for lack of promise, but for lack of a map. The true pattern is one of inconvenience. A result arrives when technology is too crude to verify it, like the early hints of the Mössbauer effect lost in the data of a previous generation. It challenges a dogma too deeply cherished, as de Broglie's pilot wave theory was overwhelmed by the authority of Copenhagen. Or it becomes entangled with a fringe reputation, its potential tainted by association, as happened with the controversial claims of Thomas Townsend Brown. These stories are not merely tales of error. They are often cases of premature truth, an intuition pointing toward a reality for which the language does not yet exist. Gustave Le Bon's black light, dismissed as an artifact, now seems to whisper of neutrinos and quantum fields. The subtle anomalies in the notebooks of Eötvös, once ignored, forced a generation to test the limits of gravity with unprecedented rigor. Even a wrong turn, like Walter Ritz's emission theory, served a vital purpose, strengthening relativity through the fire of debate. The kernel of insight might be buried, but it rarely disappears entirely. This pattern forces a profound humility. Our current understanding of physics is not a straight, inevitable highway to truth. It is a winding path through a dense forest, littered with abandoned forks and overgrown trails that might have led to different clearings. The textbooks we study are a curated museum of successes, a polished narrative that smooths over the dead ends, the controversies, and the long, quiet years of confusion. The real engine of science is not just the triumphant experiment, but the stubborn anomaly, the rejected paper, the idea that was too awkward for its time. To forget this messy, human struggle is to misunderstand how discovery truly unfolds. The next breakthrough might not be in a new particle accelerator, but waiting patiently in the faded ink of a century-old laboratory notebook, asking only for a fresh pair of eyes. The journey through these 30 forgotten experiments reveals a landscape far vaster and more mysterious than any textbook could contain. These are not just footnotes, they are monuments to the human spirit of inquiry, to the creativity and persistence that drives us to understand the cosmos. They remind us that discovery is not a straight path, but a winding road paved with brilliant mistakes, stubborn anomalies, and sometimes sheer luck. Each forgotten idea challenges us to look at the odd result in our own data with fresh eyes, to question the comfortable paradigms we take for granted. The history of physics is not merely a record of what we learned, but a map of what we chose, for 1,000 different reasons, to forget. In these quiet corners of science, sidelined by technological limits or drowned out by louder voices, clues to the next great revolution may be waiting. Perhaps the key to dark energy lies in a misunderstood notebook from a century ago. Or the secret to quantum gravity is hidden in the failed replication of a fringe experiment. This is a call to curiosity, an invitation to dig into the archives, to champion the awkward idea, and to never stop wondering about the roads not taken. Thank you for joining this exploration of science's hidden chapters, and for remembering that the universe always has more secrets to